today kind of is the, geez, the glare is really bad. It's kind of the basis of all trigonometry that you'll learn, whether it's a little bit in geometry, just kind of scratching the surface with the trigonometry that we talk about, and then when we get into your Algebra 2 courses next year, why everything works the way it works is going to be dependent upon kind of these two triangles that we talk about today. But what I want to make sure we understand is how they're developed, where they come from, and how do we set them up in ways that we're going to be able to solve problems with them easily and efficiently. Because honestly, if we can get this down pat pretty straight rather quickly, it goes by real quick. Okay? Because every problem starts kind of the same way. But before we start, though, let me show you how these things are developed. And it kind of comes from what you were asking earlier yesterday about the homework on that question 23. So if I start with something that is a square, you guys all agree that squares have 4 right angles and 4 congruent sides. And according to the last test that we took with that stuff as well, we also know that the diagonals are perpendicular and the diagonals bisect each other. And the diagonals are congruent. So all of that stuff happens with squares. Bless you. Now, as you get into this, you're going to start to see that you have inside these squares I have 2 larger right triangles formed by the diagonal. And then we also have 4 smaller right triangles on the interior. You okay with that? Now, when we have these right triangles that are created, if you just look at one set of them, and I'm just going to see if I can redraw this without too much. If I look at just one set of them, it wasn't terribly drawn for me for a diagonal. But look at just this one. It's isosceles, isn't it? Yes, no, maybe so? Yes, it's isosceles. Reason that it's isosceles is because it's got the 2 congruent legs. If it has the 2 congruent legs, then what does it have for base angles? They're also going to be what? They're also going to be congruent. Now, since it's an isosceles right triangle, you automatically figure out what those 2 base angles are going to equal. Well, if you've got 90 degrees already solved for, how many degrees are left in this triangle? Another 90. And since both of those angles have to be the same, these both have to be 45. Okay? So what we're generating here is what we call it's a special right triangle. It's called a 45, 45, 90 triangle. And just rather easily, if I say that one section here is 4, what does the other section across from the 45 have to be? 4, because it's isosceles. What would you do to figure out what your hypotenuse is? In other words, you're using Pythagorean theorem, correct? Yeah. So you would use Pythagorean theorem. 4 squared plus 4 squared equals your hypotenuse squared. Well, what's 4 squared? 60. So 4 squared plus 4 squared gives you 32. And now on that multi-view calculator, when you take the square root of 32, what does it give you for the result? Root. Yeah. The way we say that is we get 4 root 2 for an answer. Okay. that multi-view calculator will do that square rooting for you. It knows how to simplify a radical. If you don't have one of those, you'd have to crank that out by hand by trying to figure out what's the largest perfect square that goes into 32. Well, that can be broken down to the square root of 16 times the square root of 2, which is 4 root 2. So by all means, don't buy the calculator or get one ASAP and do that. It's going to get even worse when you have to rationalize. We'll worry about that later. Now, what happens, do you think, what happens now if I change these numbers from 4s to 6s? If I change those numbers to 6s, I'd have to do, what would that be, 6 squared plus 6 squared. Sorry, 5. I get 36 plus 36, which is 72. You type in your calculator right away, what's the square root of 72? 6 root 2. Very good. So what happens here is you get to develop a specific pattern that always occurs within these triangles. What's going to, yes ma'am? I'm getting to that. You're on the right track. You're on the right track, but what would happen if I did this? With what you're saying, you'd have to be able to figure out, what do you do then? How do you work backwards? And that's where we're getting. Because you're right, if these guys are 6s, this will be a 6 root 2. But if this guy is a 6, what are those going to be? And that's where we're getting to be able to figure this out, because there's always going to be a specific pattern that occurs within this type of triangle. What happens here is we have this thing that's called a 45, 45, 90 triangle. And this that I'm using this part here on the left is what I call an algebraic jig, not as in a dance jig. She would laugh if she's a dancer person. But you guys know what a jig is in terms of like machinery or building something? What is it? Kinda. A jig is something that you would use in building instead of having to remeasure something over and over and over again. If any of you guys have a deck with railings, spindles or something like that, or spindles going up your stair and all, what happens there? Yes, sir. Oh, what happens is with those things is that you don't want to sit there and reuse your tape measure over and over and over to measure 4.5 inches, 34.5 inches, 34.5 inches, and then mark it and cut it, mark it. That just takes too long. So what you do is you take a piece of wood and you screw it to like a 2x4 or something. That way you take your spindles, you slide it up next to it so it stops at that same spot, and then you cut it. Slide it, cut it, slide it, cut it. So every single cut will be identical because you created something to help you use that measurement over and over again. It's very common for stuff like that. I'm sure you guys have all seen videos of somebody in a car assembly plant where they've got the giant tools with a whole bunch of pieces on it, like a whole bunch of nuts and bolts. They bring it to the car and go, and it puts it together. That big piece that they're holding is a jig, because it's a tool that you reuse to manufacture something. All right. Every time that you're rebuilding something, you're cutting the spindles. Come on, I'll just sit up. Sean, stay behind. Sit up. Write something down. This is important. You can do this. As you go through those things, every time that you reuse a cut, every time instead of remeasuring, it just makes your life easier, as opposed to having to reinvent the wheel every time that you try to do something. So this idea of what I call this algebraic jig, it allows us to solve these special right triangles quickly and efficiently. For example, when you have a 45, 45, 90, they're going to be labeled in a couple different ways. Sometimes they'll be labeled with sides being tick marked like that with the right angle. That tells you it's isosceles. which means that these have to be 45s. Sometimes they might just have the 45-degree angle and a right angle. Sometimes they might use tick marks for the angles, and so on, just to show that it's isosceles. But what happens here is that your angles always look at a side opposite. This angle is always looking at the side opposite. The 90 is always looking at the side opposite. As you follow the lines, it's opening up to the side opposite. Following the lines, it's opening to the side opposite. So in a 45-45-90, when I draw out this thing that I'm calling an algebraic jig, notice that I have an arrow because the 45 is looking at something. What is it looking at? It's looking across from itself. So in these, the 45s always are looking at some value of x. And it happens to be x on both sides of the 45s because it's isosceles. Which means across from the hypotenuse, across from the 90, it's going to be that value of x times the square root of 2. Okay. This value of x is just some scalar. It doesn't matter what it is, because every single one of these types of special right triangles has the same pattern to it. There's always some value of 1 root 2 embedded within the problem. Now, you were asking a second ago, does it automatically mean that if the two sides are 6s, the element is going to be a 6 root 2? Yes, if it's the 45 portions. But if it's not the 45, if you're given across from the 90, something else has to happen. Okay. Let me show you what happens. Let's say, for example, you happen to have across from your 90 a value of 8. And I have this algebraic jig then. I have this 45, 45, and a 90. What I'm doing here is I'm writing down my jig, if you will, and then I'm going to fill in what side do I know across from. Well, according to our diagram that we have right now, what side do I know across from? The 90. So I know that across from my 90 is looking at some value of x times the square root of 2. Well, in this case, that value has to equal 8. If you look at that, that just generates a one-step equation. It says x times the square root of 2 equals 8. How do you undo multiply? Exactly, you just divide. So in those multi-view calculators, what you do is this. You divide both sides by the square root of 2, and it'll tell you what the value of x is. Fraction bar, 8 over square root 2, and you hit enter, and that tells you what x is, square root 2. No such thing as a decimal. It does that. You did this last year called rationalizing denominators. You had to multiply by a factor of 1 and simplify itself through. Whereas here, you press a button on the calculator, and it gives you your answer. X is 4 root 2, which means, yes, ma'am? No, because if you just take 8 and divide it by 2, you get 4. 4 squared plus 4 squared won't give me 8 squared. See where I'm going with that? So that's where this root 2 guy comes into play. Because that pattern with this style triangle will always occur. So what we're trying to do is create something that makes it easier for us to figure out the other parts. So by setting up a one-step equation, divide both sides by the square root of 2, it tells me that if I take 4 root 2 and I multiply it by root 2, I'm going to get 8. That's what it means. So everywhere I see an x now, I put 4 root 2. And that gives you my sidelines. Just by using that algebra jig, that one step. And I know it looks really weird. It's different than anything we've done so far this year, but this is where the algebra stuff comes back into play into geometry. But it's not like I'm trying to have you guys math too much. It's a matter of, can you press a button on your calculator to divide by the square root of 2? Let's do another one. Now I'll do another one with the, I'll do another one with that across from the 90. Let's say across from the 90 is 11. Well, I always write out this, my jig, if you will. And then I just ask myself, according to my diagram, across from which angle do I know? Across from the 90, I know that it is 11. So what I do is, in my algebra jig, I set x times the square root of 2 equal to 11. Now I know that looks a little bit different, because normally we would write like 3x equals 11 or 2x equals 11. But whenever we have what are called radicals, the x goes in front of the radical, because sometimes if you put it behind it, it looks like it's underneath it. So mathematically, it's more mathicate to put it prior to it. That's why it looks like that. So how do you undo multiplying? Divide. So I divide both sides by the square root of 2. Multi-view calculator gives you an answer in simplified radical form that happens to be what is it? It's different, isn't it? It's 11 root 2 over 2. And that is the answer. It's exactly what the value of x is equal to for both sides of the side lines. So that means everywhere I go back and I see a value of x, what am I going to replace it with? 11 root 2 over 2. Yep. And those are what we call exact answers. And that's what you're going to see more and more and more in this chapter. Fleckner, you're going cross-eyed on me. You okay? Yeah. You seemed like you were a little upset about it. Are you upset about this? No. All right, just making sure. Like, you kind of. Okay, so do you need me to blow this up? I'm not like literally blow it up, but if you need me to do this. Is that better? Okay. I was worried about you. Did you need me to highlight it at all? What do you think changes now? That's the right answer. Nothing. What kind of a triangle is it? Well, let me rephrase this. What's the only one we've talked about so far? The special right triangle of now you know across from which angle? We know across from a 45. So does it matter which one I write in that I know across from? Nope, not at all. I know that across from one of my 45-degree angles is the value of the square root of 3. Well, according to my algebraic jig, that means that the value of x is equal to square root of 3. So everywhere I see an x, what am I going to write? Square root of 3. So what do I do with that? Square root of 3 times the square root of 2. What do I do? Put it in the calculator, you type square root of 3 times the square root of 2, and you get square root of 6. It does it for you. It leaves it in the simplified radical form. Right. If I put shoe for a side length across from 45, the other side would be shoe. And across from the 90 would be shoe root 2. What? What? I have shoes. I have shoelaces. I know shoe. I know Mrs. Shoe. I know Mr. Shoe. I know children's shoes. I have children's shoes at home. Not shoes, children's shoes. My own children's shoes. Not mine, but my children's shoes. I choose you. I did. It was kind of fun. Sorry, collector. Let's go to yellow. Yes, ma'am. No, because so, what kind of triangle is that? Equilateral. Okay, I'll give you its isosceles, but more specifically, it's equilateral. In an equilateral triangle, what do all the angles measure? Yes, they measure the same, and that same measurement is 60. Okay. Also, from that, one of the things that we've done before is we drew the altitude. The altitude of an equilateral triangle, or isosceles, is drawn from the vertex to the side opposite, and it is perpendicular. If you recall that the altitude bisects the side that it runs into for these types of triangles. So I get, let's do this, these two parts are going to be the same. It also bisects the angle up top. So if it was 60, both those angles become 30s. So what we're generating here, ladies and gentlemen, is what we call a 30, 60, 90 triangle. And what we do is we started out with this. If I say I have side lengths of 2 and 2, that means this whole thing was 2, which makes each individual piece how much? 1. Now, I need to figure out some means to know what the height of that guy is. So let me redraw this real quick on a clean sheet. I redraw this. We had a 30, a 60, a 90, a 1, and a 2. Is the missing side length a hypotenuse or a leg? It's a leg. So I'm going to use Pythagorean theorem to figure out what the side length is. So let's just call it x for right now. And I'll get x squared plus 1 squared is 2 squared. Well, what's 2 squared? 4. What's 1 squared? 2. What? It's 1. So you get the equation, x squared plus 1 is 4. What do I move first? 1. So then I get x squared is 3. And then how do you undo square root? That means that the side opposite the 60 becomes the square root of 3. I notice I'm not putting plus minus there because I can't have a negative second length. That's why I just kept it as positives. You okay with that? What happens now is that we've just created another special right triangle. This one is what we call the 30, 60, 90. And this one follows the pattern of, make another jig. This one forces you to be able to do two separate algebra problems. Oh, sure. What? Am I too much? Okay, grumpy. So, again, we go with the idea that the 30-degree angle is looking at a side of 1. The 60 is looking at a side of root 3. The 90 is looking at a side of 2. But every time we're going to throw x in there. What's 1 times x? Just x. So we say that across from the 30, some value of x. Across from the 60, that value of x times the square root of 3. And across from the 90 is 2 times x. And it's going to work the same exact way as the 45 stuff did about what angle do you know opposite you, or what side length do you know opposite you, to be able to figure out what value you're working with. For example, if I go back to my diagram here, I erase my sides for right now, and I do something really easy. And I say that across from our 90 is 10. If I say that across from my 90-degree angle is going to be 10, excuse me, that means I know that this value, this simple jig here, the 2x has to equal 10. How do you undo that one-step equation? Divided by 2, good. If you divide that by 2, what do you get for x? 5. Which means everywhere I see an x in the other parts of the jig, where do I put? 5. That's how this stuff works. It is super fast. As you go through this jigsaw, you're solving at most a one-step equation to go for. That's all we're worried about here, guys. It is so quick to work with. And it is so quick. The only weird one with this one is, well, can I erase my 5s real quick and put up different numbers real quick so I don't have to redraw? You okay with that? Let's say we know that across from our 60 something different. Let's say across from our 60 in this case is equal to 12. If I say that across from my 60 is going to be some value of 12, and I want to reuse this jig, excuse me, 30, 60, 90. If I know opposite my 60 is equal to 12, which one of these values in the jig do I set equal to 12? 60. So I know that I'm going to have a one-step equation, x times the square root of 3 equals 12. How do you undo multiplying by the square root of 3? You divide by the square root of 3. Oh, sorry, sorry. You divide by the square root of 3. In that multi-view calculator, if you divide 12 by the square root of 3, yeah, you sort of back in my statement. What does it tell you you get? What do you get? Say it. 4 square root of 3, very good. Which means that the value of x equals 4 square root of 3. Which then, everywhere I see an x, what am I going to put? 4 square root of 3. What do you think 2 times 4 root of 3 is going to be? Watch that. 8. Sorry, I was lifting heavy things. What's that? 8. Oh, careful. Use your calculator. Just hit 2 times 4 root of 3, and it gives you an answer. 8 root of 3. It's that quick. Every problem is exactly the same. Every setup is exactly the same. All you have to worry about trying to do is set up the algebra jig to match what problem you're working with. All right? Let me show you something here. What's that? Am I right? That's what I want to have you guys continually drawing up, drawing this over again. Oh, this was. Can you reach that high?
Yeah. No.
Yeah, Billy. I think it's an extra one for you. I get to do 10, which means I bet you it's that. You don't want it. Take a look at number one. Number one.
Oh, wow.
Number one, what type of triangle is it? Height. So 45, 45, 90. So first thing I do is next to my problem, I write down 45, 45, 90. I fill in my algebraic jig. According to the diagram, you know opposite which angle of 45. So that means I'm going to set one of my 45 values equal to, in this case, 7 root 2 over 2. So everywhere I see an x now for the rest of these problems, what am I going to put? Yes, sir. Yes, ma'am. 7 root 2 over 2. And then I know that this is going to be 7 root 2 over 2 times the square root of 2. Just to be cautious, that's why I like having this ugly problem to start out with, is how do you type that in the calculator? Well, you quite literally type it the way that it looks. Fraction bar, 7, oops, I'm sorry, right, 7. 7 root 2 over 2 times the square root of 2. I'm typing it exactly the way that I wrote it down. That's another big thing that I want you guys to start being careful with. Anytime you have these weird math things that you're going to put in your calculator, I'm going to ask that you guys write down what you're about to put in the calculator before you put it in the calculator. Because it is so easy to flip-flop digits and write down the wrong and type in the wrong thing. And you get 7. What? Well, so across from the 90 is 7. Okay? You're literally filling in blanks off the algebra tree given the sideline. Look at number 3, directly below that. Number 3, what kind of a triangle is it? It's a 30, 60, 90, isn't it? For 45, 90. In 30, 60, 90, it's something different. And those of you guys that were out taking the test and stuff, this will take maybe a couple extra times to get it down, but it's pretty self-explanatory after a while. So I know in question number 3 is a 30, 60, 90. The reason I know it's a 30, 60, 90 because there's a 60 in it. Okay? So across from the 60 is what, according to the diagram? 5 square root 3. So that means I'm going to set across from the 60 portion here equal to 5 root 3. 3. Okay? That's the ratio of the sides. We're taking your stuff. Don't worry. Okay? Now I have a one-step algebra problem to solve for. How do you undo multiplying by root 3? You divide. So in your calculator, what do you think 5 root 3 divided by root 3 is going to be? 5. That means that x is equal to 5. So everywhere I see an x in this algebraic jig, what am I going to replace it with? 5. So my side lengths, my missing side lengths are 5 and 10. Okay? It's the same thing over and over and over again. Go over to number 9. Number 9, which type of triangle is it? 30, 60, 90 again. It's a 30, 60, 90. So I write down my algebra jig. And across from which side length do I know? I know across from the 30, across from what angle do I know is the 30. So that means that across from the 30 is some value of x, and according to our diagram, that value of x is now equal to 2 root 6. So everywhere I see an x in the rest of the algebraic jig, what am I going to replace it with? 2 root 6. So in the calculator, you quite literally are going to type in 2 root 6 times the square root of 3, 2 times 2 root 6 to get your missing side lengths. So when you type in 2 root 6 times root 3, I think you get 6 root 3? 6 root 2, sorry. Thank you. Oh yeah, you're right, bring out the 3's. So here you get across from the 60 would be 6 root 2. And here it's 4 root 6. And those are your missing side lengths. Using that multi-view calculator, it gives you all your answers in that simplified radical form. Knock this out, but trust me, what I want you to do for every problem is write out that algebra jig and set up the algebra. It shouldn't take that long, okay? Thank you guys. Sorry I ran late.